Hi, it's Paul Andersen, and this is Crosscutting Concept 5. It's on energy and matter, and how energy and matter flow through a system, how they're recycled, and how they're conserved over time. And so our Earth constantly gets energy from the sun, and a lot of that eventually becomes heat. But a lot of the things are recycled on the planet. A lot of the matter, like water, is recycled. In other words, it's used over and over and over again. And so it's important that our students understand how energy and matter work, because in science, it allows us to properly study and understand systems. And systems are super important in engineering because it allows us to control the system and therefore improve the design. And so what is a system? Remember, that's separate from the universe. It's a part of the universe that we choose to study. And it could be as simple as a greenhouse or a machine. Your brain could be a system. And even the whole Earth could be a system. And so basically, it's something separate from the universe. And so if we have a system, it can be acted on by forces outside the system. But since we're talking about matter and energy, that matter and energy has to get into the system, and then a lot of the time it has to get back out of the system as well. And so we need input and we need output in order for matter and energy to be used by a system. And so what is flow? Flow is essentially matter or energy moving into a system, moving through the system, and then moving out again. And what is a cycle? A cycle is when matter or energy are recycled over and over again within a system. Now, one concept that you want to make sure your students understand is the idea of conservation of mass and conservation of energy. In other words, the amount of energy that goes into a system is going to equal the amount of energy that comes out. The amount of matter or mass that goes into a system is going to equal the amount that comes out. And so this idea of conservation is super important and totally true. One little caveat to that, remember, is that we can convert matter into energy, but that rarely happens. And we're not going to see it until the end of this slideshow. And so let me give you a real example of this. So energy flow. You're probably familiar with the greenhouse effect. And so what is the greenhouse effect? Basically, since we have an atmosphere, energy that comes in, so solar energy, instead of just being reflected back out into space, some of that is converted into infrared radiation. Some of that's converted into heat. And so if we look on this chart, there are 343 watts per meter squared of energy that's coming from the sun. And a lot of that is just going to be reflected back out, either at the top or in the middle of our atmosphere, or even off the surface of the planet. And so that makes up about 103 watts per meter squared that's being bounced right back into space. What happens to the rest of the energy? Well, that's going to hit the planet. It's going to be absorbed by the planet, and it's going to be converted into something called radiation or infrared radiation or heat. A lot of it's going to hit greenhouse gases and get bounced back again to the Earth. And so basically, the energy doesn't stay here. The energy is eventually going to leave as heat, but we're converting more of that visible light into heat, and that keeps our climate really, really warm. So for example, Mercury, even though it's much closer to the sun, is going to be really, really cold because they don't have an atmosphere that can do this. But if you look at these numbers, it's going to be exactly equal to the amount of energy that we're losing that we gain. It's just that it's converted into heat. If we look at cycling, how does that work? Well, one cycle that you're probably familiar with is the water cycle. In other words, the water on our planet is constant. The water that we have in our oceans and lakes and in the clouds and in the groundwater is the same. In other words, we have a set amount of matter, and so it's recycled on our planet. Sometimes it's in the clouds, sometimes it's in rain, sometimes it's in runoff, sometimes it's in the ocean, and sometimes it evaporates back into the clouds again or moves through plants through evapotranspiration. But the amount that we have is the same. When you have a glass of water, that water, the molecules in it, used to be in an ocean a long time ago, and used to be in a cloud and used to be in rain. It's just recycled over and over and over again. But the amount we have is conserved, or it stays the same. Why is it important in engineering? Well, think about it. Let's say you're trying to design a solar-powered car. It's important that you understand how much energy is coming in and how we convert that to other forms of energy. We can store some of that energy in a battery, and we can utilize that some of that energy using electric motors. And so there are some misconceptions that I want to talk about in relation to matter and energy, and they're just going to jump up, and it's important that we address these. And so here's something that's interesting. When you go to bed at night and you wake up in the morning, if you were to weigh yourself, you would find that you're going to weigh about 1/2 pound less in the morning. In other words, you lose weight at night. And if I were to ask you where it went, a really common response I get from students is that you burn it up as energy. Now know this, we can't convert matter into energy. It happens very rarely, and again, we're only going to talk about it when we get to the end of this video. And so where does it go? Well, the matter is released. You're breathing it out as carbon dioxide and water vapor, and so you're losing matter from your food there, but we're using some of the energy that was found in the bonds of that food that we had. And that's what we're using to keep our heart beating, keep our body alive. Here's some other misconceptions. When you say you're drinking an energy drink or you have an energy bar, there's this idea that there's some secret energy that's found within it, and that's not true. The energy is going to be found in the chemical bonds of the food, and we can release some of that energy and convert it into another form, but it doesn't have some certain kind of energy in it. And how do we do weight gain? In other words, where does a tree get all of its mass? If you were asked that question to students, they would say maybe the mass comes in from its roots and water, maybe it's minerals coming into the roots, but they don't see where the matter is going into the tree. The matter is coming into the tree in carbon dioxide. So the matter is moving in through its leaves, and then it's using that carbon dioxide to make the wood, and eventually we can lose that again. And so there's some real weird misconceptions about energy and matter, and that's important when we think about the progression of which we're going to teach this. And so we want our students to understand how matter and energy interact with one another, but it's important that we don't talk about energy right away. In the lower elementary grades, we should just be talking about matter and how matter can flow and how matter can cycle. We shouldn't talk about energy until we get to middle school, and then we should be really careful about how we talk about energy and making sure that we're using the right terms. And then finally we get into conservation. There's a lot of cool labs you can do so you can study how matter is conserved, and even energy is conserved as well. And so where do you start? What's the progression? In other words, how do you start in the lower elementary grades and work your way up into high school? How do you get your students studying matter and energy, in other words, throwing darts at the dartboard, but getting better and better over time? Well, you should start with matter. And it's really understandable to students what liquid, solid, and gas is. And so you can deal with forms of matter and what matter is and what it's made up of. You could start with that at the elementary grade, at least different forms of matter. That's pretty straightforward. As you move through elementary, then you should bring forward these ideas of matter flow and then matter cycling. But we shouldn't really talk about energy yet. We'll save that until they get to middle school and high school. And so what's an example? Well, this plant right here is taking in matter from its roots. It's taking in water, for example. That water is going to move through the plant, and then it's eventually going to evaporate off the leaves. If we were to put a bag over that plant, we're going to collect a lot of water vapor inside it. And so we could study how water is flowing through it, but we could also study how other matter is used. And one that's really misunderstood is the carbon cycle. And so I would talk about the carbon cycle if it were me. Carbon, remember, is mostly going to sit in the atmosphere as carbon dioxide. And where is it going to go? Well, it's going to be used by plants. Plants are going to take it in through their leaves. They do photosynthesis, and they use that to make the plant. Eventually, we're going to release that because we're going to eat plants or things that eat plants. And then we're going to release that carbon in that food as carbon dioxide. It goes back into the atmosphere again. And so that's a great thing to talk about. The amount of carbon we have on our planet is the same. It's just going to be recycled over and over again. As we move into middle school, then we can really start to talk about energy. And so a good place to start is talking about metabolism. And so our food contains energy. It contains free energy that we can use to do things. And so how does that work? Well, you're taking in food, carbohydrates, fats, things like that, and then it's eventually going to leave you. In other words, the amount of matter that we take in and the amount of matter that we're giving off is going to be exactly the same. In other words, we have to account for all of that matter that comes in and goes out. So what happens to the energy? Well, in cellular respiration, we can release some of that potential energy that's found in our food, and we can release that during metabolism, and we usually convert it into something called ATP. But we're not somehow creating energy in the food, or it doesn't have energy. You probably want to address the difference between mass and weight at this point as well. And so mass, remember, is a measure of the amount of matter that we have, but weight is going to be the gravitational attraction. In other words, how much the Earth is pulling on us. And so mass and weight are going to be the same if you're on our planet, but if you were to move to the moon, your mass stays the same, but your weight's going to change because the gravity is going to change. And so a way to think about that, this hot air balloon, if you were to put it on a scale, since it's buoyant, it's not going to weigh anything. But that doesn't mean that it doesn't have matter, it doesn't have mass, it doesn't have inertia. We can study this in the lab as well as we move into high school. We can look at the conservation of matter. And so a really simple experiment is to take a given amount of water, and we could mass that, get its mass. We could take a given amount of sugar, and then we could add the sugar to the water, dissolve it, and then we can measure their combined mass. And a lot of students think it's somehow going to increase or decrease. The sum of those original masses is going to equal the sum of the sugar water. In other words, we're just dissolving that sugar in the water. And you could even do chemical reactions. So a typical one would be to take water and an Alka-Seltzer tablet. You take the mass of the water and the Alka-Seltzer tablet before you put them together. You have to make sure, since we're going to produce a gas, that you have a bag around this or you do it in some kind of a closed container. But basically, we take the matter before and after, and we're going to have the same amount of matter, or conservation of matter. What's in Alka-Seltzer? It's basically baking soda and citric acid. And so it's that same old vinegar and baking soda reaction that you've seen before, and that'd be another thing that you could do in the lab. And then finally, we're going to get to the nucleus. And so what is the nucleus? It's at the center of every atom. It's made up of two different particles. It's going to have protons. Those are going to be the red ones here. And then it's going to have the blue ones, which are neutrons. And so these together are called nucleons, or both of those. It just means that they inhabit the nucleus. And one thing that should make you think a little bit when you're thinking about the nucleus is that we have all these positive charges on the inside. And so you know that positive charges repel each other. And so how do we get them to stay in the nucleus? Well, there's a force that many people are not familiar with. It's called the strong nuclear force, or the strong force. And basically what that means, it's a force that holds these nucleons together and holds them in the nucleus. You don't sense it because it only occurs at really close proximity, but there's something that's holding it together. And so we can also have what's called a nuclear reaction. So unlike a chemical reaction, what we're doing is we're combining two nuclei, or one nuclei and then another particle. And so this is an example of one. We've got lithium. Lithium is going to have 3 protons and 3 neutrons. And then we have deuterium. Deuterium is going to have 1 proton, but it's also going to have a neutron. And so if we were to put those together at the same place at the same time, we're going to form an unstable nuclei, and then it's going to basically going to decay into 2 alpha particles. And so we write that like this. We have our lithium here. It's got 3 for an atomic number and a mass number of 6, plus our hydrogen, or our deuterium, and basically it's going to break down into these 2 alpha particles, which is really a helium nuclei. What's coming out of that? Well, we're converting mass. In other words, we're changing the mass. And as we do that, we're decreasing the amount of mass and we're releasing energy. And so where does the energy in a nuclear bomb come from, or a nuclear reactor? We're actually converting mass into a smaller amount of mass. And even though it's infinitesimal, we're releasing a huge amount of energy. And so that's matter, that's energy. It's really cool, and I hope that was helpful.